Well, we're going to go ahead and get started because I have a few things to go over for you folks today here. So first off, welcome to Think Big, Making Massive Assemblies Sing in SOLIDWORKS. Two quick little announcements before we get started. First off, last year we had a presentation called Think Big, Making Massive Assemblies Sing in SOLIDWORKS. This is not the same exact presentation. This is more of a part two, if you will. Ricky Wynn did the presentation last year. That was great. I highly suggest going and checking it out. It's on our YouTube channel. This year, it's going to be kind of a continuation of a similar theme. The second announcement, very exciting here. I actually have a special guest speaker with me. Put your hands together for Jean-Paulo Bassi, CEO of Dassault Systems. Get Jean-Paulo in here. What's that? He's not here. He's in Europe. That makes sense. Okay, so instead, filling in for him, we will have Ryan Navarro moderating the comments and questions here. Ryan is going to be a great help, and you'll probably see him a couple other times here because I think he's going to get the most moderator award or something like that for today. So a little about myself here. My name is Sean Mars. I'm a senior applications engineer as well. I work here out of the Beaverton, Oregon office in the Portland area. I've been with Hawkridge Systems for the last 6 years. My favorite SOLIDWORKS related product is flow simulation. So if you want to talk about that with me, then I would love to. And I guess in the theme of extreme here, my hobbies are martial arts. Been doing those for a number of years. And I just recently got back into downhill skating or longboarding. And in my area, we have a longboard run. It's also a bike run called Zoo Bomb, and I actually live right up in this area too. And so I've been able to do that, which is really exciting because it's something that I thought I would never do. So anyway, that's enough about me. Let's go ahead and talk about this presentation here. So what are we going to be doing today? Well, I'm going to be splitting into kind of 3 parts. We have the main section at the end, but before we can get to the good stuff, I'm going to be talking about how do we measure performance in an assembly. So we're just going to take it to a couple basic parameters that we can use to understand how what we do to the assembly is going to affect the change and benefit it. Then we're going to be talking about our classic troubleshooting tools, how we actually go and sniff out the problems, essentially. And then I'll get to actually streamlining. So what are some techniques that we can use to not just simplify an assembly, but just best practices for making things run more smoothly. So first, let's talk about how do we measure performance. So I want to first go through file size, right? File size is oftentimes, something that we can easily measure and see, okay, what did our changes do to affect the file size of the assembly or parts or, maybe the entire folder of components. So I just want to make clear that the a SOLIDWORKS part, you can think of it as breaking up into 3 parts that we kind of have control over. So you have the parasolid, which is essentially just the geometry, the mathematical model of your parts. You have your tessellation, which is the approximation of that geometry that your graphics cards give you. And then finally, we have the parametrics, which is what I think most of us actually think of as what the part is. It's the instructions that SOLIDWORKS uses to build the part. And so based on what we can do, we can actually vary these 3 things and affect the file size, which could then affect open times and things like that. All right, next, let's just quickly talk about what happens when you open an assembly. So I'm just going to stay in the assembly realm here and not get to the continued process when you open up the assembly drawing. But the first thing that has to happen is you have to load all the reference parts. That's pretty obvious. You have to get the part files, the sub-assemblies, things like that. But the mode that you open things up into and any simplification measures could really affect this. So for instance, we were just talking about the 3 parts to a file. If you open up something in lightweight mode, it's not bringing in the parametrics. So it's only bringing in the geometry and the tessellation. Then it has to go and update parts. So if you've ever opened up something in lightweight mode and you're like, wait, why did some of my parts or sub-assemblies not open up in lightweight mode? Well, one reason might be that they're just out of date. So if you add a feature to a part, the next time you open up an assembly, it's going to be resolved until you save that assembly. Then it can start opening up lightweight. All right, then one of the big pieces we can control is it has to go through mates. So it has to deal with any mates that need to be solved at the top level. And the biggest thing to do with this is sub-assemblies, right? So sub-assemblies hide and store lots of mates down inside those sub-assemblies that don't need to be evaluated at that top level assembly unless you have flexible sub-assemblies. The next thing it's going to do is it's going to update any in-context features. So if you have externally referenced components or you have assembly level features, and you can see that kind of hidden underneath here, the next thing, if I go back up here, it cycles back up to solving the mates again if they're referencing assembly features. So if you can avoid putting a mate onto a patterned component, like the instances of those patterns, that's good because you don't want this to have to cycle back up through there. All right, and then finally, we're going to be, the ultimate nightmare. Finally, we're going to be applying appearances to bodies and faces. So this is another thing you can control. A lot of times, appearances will be attached to faces, and there can be tons of them in there without you really realizing. And that's something we can deal with, and that can really affect open time quite a lot. Okie dokie. Next thing is rebuild. So there's really only like two things I really want to mention about rebuild. Is one, rebuilding does not rebuild all of the features at the part level. So especially if you think about lightweight mode, I mean, lightweight mode doesn't even load the parametrics, doesn't load those features. So the assembly rebuild of whatever assembly you're working in is really going to be looking at those features, which are like mates and assembly features, external references, anything like that. And then it has to generate graphics. So, all right. And lastly, dynamic view manipulation, which is essentially just the fancy pants way of saying panning and rotating and zooming, anything that changes what our screen needs to show us, right? Your graphics card's gonna have to work on this. So having your updated graphics card driver, we're probably always being told. And then in the last couple of years, we have that graphics pipeline, which can actually really improve your graphical performance. In terms of your control over things, you have control over the number of bodies and whatever kind of detail that you could pull out of those. So any kind of simplification measures or anything like that will help, or even just hiding things. If you can't see it on the screen, your graphics card's not creating it for you. Okay, so those are our basic measures: file size, open time, rebuild, and our view manipulation. All right, so our troubleshooting tools, these are the classics. If you've ever done any kind of assembly, if you've ever sat in any of these assembly talks or went to training or looked it up, you've probably come across performance evaluation and assembly visualization. And the reason why they always keep coming up is because they really are that important. I mean, they are the best tools to sniff out your problem parts. And a lot of this, you'll hear like the 80-20 rule quite a bit. And it's basically saying like 80% of the benefits come from fixing 20% of the problems, or there's a lot of different variations of it. But this is going to help us find the 20% of components that we can work on to get most of the benefit. Also, as a side note, if you didn't know, 80-20 aluminum, that company, like with all the extrusions, it's named after that rule. I always thought it was something to do with dimensions or something, or maybe like, I don't know, aluminum content or something. So, okay. So what are we going to be doing today? I have a big assembly. I don't know if it's necessarily massive on the scale of some people's range here, but the point was that I didn't know anything about this assembly, and I wanted to go through trying to simplify it. So what can I do to make this thing run better? So let me go ahead and show you this real quick. So get out of here. Okay. So you should be able to see my SOLIDWORKS now. This is an Arenda jet engine, and I got it off of GrabCAD. So if you've never used GrabCAD before, it's an online repository. It's like a public library of CAD models. And I just went up there. I was like, okay, I want something that wasn't made by SOLIDWORKS, wasn't made by Hawkridge Systems, wasn't made by me. I don't know anything about, and I want to open it up and start working on it. And I also had a goal of doing the least amount of work, because I can only show you guys so much. I also, I don't want to make this a thing where, okay, you need to spend your whole life working about every little issue and every little area where you could possibly simplify. Where are things that you can quick and easily change or affect the model's performance. And the other part about it is it's a really great model. I wanted to make it so that this is still a workable model, something that we can be affecting change on, and we can continue working on it, right? On top of that, it's a GrabCAD model, which means it's not my model. It is Dave Rutland's model. So thank you very much, Dave. It's a beautiful model, as you guys will just see it more and more and more. And it really, if you want this, you can go on GrabCAD. You can get it yourself. Just look up Arenda Jet Engine. It's a Canadian jet engine company that I do not believe exists. But Dave literally just bought the detailed drawings online and then started making everything in SolidWorks. And it's great. So go follow Dave. Maybe give him some work, because I guess he's a self-employed service engineer. But I wanted to not mess with Dave's model too much, but just see where I could get improvements. All right, so what are we going to do? Well, this is the steps that I went through in order to try to improve the performance of this model. And once again, a lot of these things aren't even like tools or like really big major changes. Some of them are just things that you have to kind of deal with in terms of just any model or assembly or things like that. And once again, the name of the game is not messing up Dave's great model here. So the first thing that I did is I went into image quality. So I started this because as soon as you open it, you can make this change and you can get a lot of benefit from it. So Dave actually originally, if I get out of here, all right, so the original location of this, if you go into your document properties, image quality, was about halfway. And I know, this is another thing that you've probably been told over and over and over again: watch your image quality, settings, and don't have it up there. But all of Dave's models were about halfway, which leads me to believe that it was a template. So that's really the best place to start, is changing your templates to be lower. If you're using the SOLIDWORKS defaults, it'll probably be somewhere around here. But watch out, because sometimes we pull this slider up because we want to get a better screenshot, or we're sending it off to the tessellation off to a photo renderer or something along those lines. But you want to go ahead and pull that down eventually, because it has a huge impact on the file size depending on how detailed the tessellation needs to be. So my general rule with these things is any kind of small round thing relative to the rest of the model is going to be your problem. So the biggest culprits are always bolts and ball bearings, where the ball bearings are actually modeled, because they're small and they're round. Small curvy stuff is a problem. This has hundreds of fasteners. There's like over 900 fasteners. And then it also has hundreds of fins. It's like little turbine fins and compressor fins and things like that. And they're relatively small and they're definitely curvy. So the only thing I really want to mention here is there's this option, apply to all reference part documents. Just as a heads up, you need to have things resolved, because you need to have them loaded on your computer when you make this change, if you want that to push down to all those part files. And it's part files, not assemblies files. Now, this will still, whether or not you have it fully resolved, it will still affect this assembly. So you'll still get the benefit here. But if you wanted to like automate the process to push it down into further lower levels, then you want to have them resolved when you do that, or do it per sub assembly if that's easier on your computer. Now, the other thing that's really nice is if we go into one of our tools here, so performance evaluation on our evaluate tab, performance evaluation has kind of these general areas here, so I can see which files are opening the slowest. I have my general graphics info, so which ones are the graphically heaviest. And then right below that, I have my shaded image quality. So this will tell me, okay, what components are still at a higher or a medium in this case, because there's also a high section here. And you can see these are all assemblies. So once again, I resolve the whole thing. I move that slider and then saved the files here. But my sub-assemblies still need that work. And that's just something that as I go and work in those sub-assemblies, I can go and make those changes there. Okay, so in terms of how much did this actually change things, right? So I'm harping all on this image quality and you're going, oh, come on, Sean. Well, where Dave's original settings looked like this, so about halfway, and it was 125 megabytes. when I pulled it down to this fourth kind of tick mark here, it went from 125 megabytes to about 77 megabytes. So almost a 50 megabyte swing just from pulling that slider down. Now, this is just the assembly files. Remember, all those other part files and things like that, they can also pull that down. And the amount of small curvy things you have will be a huge influence on this. If you have a cube that has a bunch of flat sides, doesn't take a lot of graphics triangles, not going to see a big input or a change there. Now, let's see what happens if I put it down to the lowest level. So if I pulled it down to the lowest possible level, it goes down to 37 megabytes from 125. Now, the problem is it looks terrible. And essentially what that slider is doing, it's the deviation from the real geometry to the tessellated geometry you're seeing on your computer. So when you have things down this far, like once you go past that fourth tick mark that I have it set at, it really starts to degrade pretty quickly. And in that case, it really can make a huge, it can make it difficult just even select things, right? So where edges seem to be on your screen won't actually be where they're at. So that can make it difficult for obvious reasons. Okay, so let's move on. What did I do next? Okay, I hid the hardware. So that's another thing that it's a pretty quick, easy thing to do. And remember, a lot of these things is I'm saving a lot while I'm doing this. I was opening and closing things a lot. And I wanted to try to speed up that process as much as possible. So hiding all of the hardware, all those small curvies, essentially it's the same situation here. Not only is it going to be easier when I'm doing all my view manipulation, panning, zooming, rotating, all that stuff. But there's those, you can uncheck loading those hidden components when you open things or after the fact. So that's essentially going to treat hidden components as suppressed until they're told to be shown. So that initial flip to being shown will be slower, but until you need to do that, they'll basically act as if they're suppressed. So doing this is pretty easy. So if I go off into, let's go back to display state 1 here. And then what I'm going to do is use my selection tools. So up here or on your F5 filter toolbar, if you use this, or if you just want it on the screen, you can either use select toolbox, but Dave didn't use the toolbox. He actually made all of these parts. Like every single part in here, as far as I could tell, was made by Dave. So, I mean, hey, that's great. Select by size is the next best option just because relative to the rest of the assembly, hardware is usually small. And then essentially I use that as my first run. And then as I was working, I just keep adding to the display state by using like select identical components. So essentially all I would do is say select by size. I use the dynamic option here so I can see on my screen where they're highlighted, and then you can put a percentage in here. So let's say if I put like 1% in, I get just under 400 components. 3% seem to be about the right place to go, so about 974 components. The one downside to this this tool is you can't rotate while you're in it. So kind of the position you're in is what you get right now, but once you say okay, then it's just selecting and then right click and hide. And remember, if this is saved in display states are a lighter weight than configurations. They also switch back and forth faster. And then anything else that I'm hiding as I go will just continue being saved in that display state. Now, when you're doing something like this, and I just selected 974 components, how do I know if I didn't over select things? Well, essentially what I do is I go over to show hidden components on the assembly tab, and that will flip flop. Everything that's hidden will now be shown. Everything that was shown will be hidden. And then you just select components that you want to basically toggle back to being shown. So if there's anything that was overdone with this auto select option, you can fix it with show hidden components. And I actually have a little screenshot of that just because it's actually just cool looking. So go down here. This is what it looks like when you do show hidden after that. I have a good question here. If they're acting as if they're suppressed, will other components lose reference to that part? It'll probably suppress the related mates and things like that. So half the time I'm using it stay loaded, half time not. Remember, it's just a display state, so it is pretty quick to flip-flop back and forth. For this presentation, I just have everything resolved because there's a lot of operations that you still want things to be resolved for, and I don't have the time to be flip-flopping back and forth. So, okay, so in terms of the actual effect on this, this is a snapshot from assembly visualization. Our visualization tool, which I'll get into in a moment here. But you can see the total graphics triangles of the assembly. So before they're hidden, they're just under 8 million graphics triangles. After just hiding all those hardware components, it was about 4.4 million. So not quite half reduction, but it's still huge in terms of what my computer has to deal with, especially while it's running this webcast kind of thing here. Now remember, your mileage may vary because it's dependent on how much hardware you have, and Dave had very detailed bolts, so that hiding them really helped a lot. Okay, let's move on here. Okay, next thing it did was rigid sub-assemblies. So Dave had 4 flexible sub-assemblies in this file. Now what that does is it brings all of the mates from those sub-assemblies up into the top level essentially for when they're being solved. And so I want, that's going to affect your rebuild. It's also going to affect your open time because it has to deal with those mates. I have a good question here about number of mates in a large assembly. I will talk about that in just a moment because you might be seeing this under 300 mates thing here. But real quick, how do you do this? It's really easy. This is the moment where you do want to use a configuration. So I didn't use the configuration for the hiding components, and I didn't want to suppress those components because that hardware wasn't actually put in at this level. They're all in the sub-assemblies, so suppressing them will affect those sub-assemblies. Hiding them is just here in the file. Once I get to choosing whether or not things are flexible or rigid, well, that is something that I need to that is something that I need to have saved in a configuration. So that's where it made sense. Okay, time to make a new configuration. And I didn't just make them rigid in the original because remember, I'm trying not to affect Dave's files too much because I don't know why he had them flexible. Maybe he had a very specific purpose. He wanted to check clearances or collision, or he wanted to do some kind of animation or whatever it is he was doing. I left that alone, and it really actually didn't increase the file size very much, just adding this one configuration. It was like a couple megabytes adding the simplified one. And then in terms of the effect, well, if you go into your performance evaluation, there is an rebuild performance section here, and it'll tell you how many mates were evaluated when it's rebuilt. You can also use this little rebuild report here, and it'll kind of break down the last rebuild to see if it was really slow all of a sudden, or you're not sure why. It'll break down those little steps and what caused the slowdown. Now, compared to the flexible subassembly, it had 648 mates. So it went from 648 down to 38 once by making it rigid. Now, once again, mileage may vary because this is very dependent on what your mating scheme looks like. Dave did a really good job of having sub-assemblies at the top level of this, but there's not many sub-assemblies lower down. So the depth of this assembly is not very far. So we could probably improve performance at those sub-assembly levels by having further sub-assemblies down there. Now let's talk about this 300 mates situation. So I have said 300 mates many times, and I didn't really know why I was saying it, just something I heard, it made sense. Okay, what it really is that the time it takes to solve mates is proportional to the number of mates squared. So having 300 mates is a lot better than having 400 mates because 300 squared versus 400 squared. It really just becomes you want to have the least amount of mates possible, but having a large amount is really going to degrade performance a lot faster because it starts to get, it's exponential. And then as Ryan's saying in the chat there, any of your standard mates and ones that basically any of your standard mates solve faster, and it doesn't actually benefit you to have a fully defined assembly. So you don't need to do things like locking the rotations on your concentric mates. If you can avoid distance mates and angle mates, those are slower. Any of the advanced or mechanical mates are also slower in general. But if you can remove number of mates, so if you have like someone's saying like, what about like width or symmetric or maybe profile center or something? If you can remove the number of mates by having those ones, you could see a benefit there. Okay. Okay, next thing is just like a no-brainer. Fix your errors, right? So your mate errors. So half the time, most commonly, these are going to be missing references. So if that's the case, oftentimes SOLIDWORKS can replace many of them on instances of the components by fixing one of them. So, it's kind of one of those like, go clean your room and then you can go play with your friends situations. You should go fix your mate errors. Dave didn't have too many. It was just missing references, mostly with bolts. And some of these actually were fixed just by doing Control Q rebuilds in the sub assemblies that they were broken in. But if you have a true over-defined mate situation, that is something you want to figure out, because the mate tool is actually really good at having over-defined mates where they are in accordance with each other, so they don't conflict. But once they're conflicting, then that really slows down your rebuild or anytime the mates have to be solved. So here is just a quick little bit of information for you. So just go ahead and just read through that while I get a sip of coffee here. No, don't read it through that. Okay, so that is a solution from the SOLIDWORKS knowledge base, but really all you have to know is that part of solving mates is that SOLIDWORKS has to figure out the order to solve mates. So it has to parse this mate group here. And if errors are found, it has to go process those mates again and try to see if it can find a good result, or if it needs to put up errors or warnings. So when you have a true over-defining case where things are conflicting with each other, then this will be much slower, right? And especially, I love this official like solution from SOLIDWORKS tech support where they have the least bad solution. So there's that. But if you have things that are conflicting, that's just one of those, hey, who wants to see all those crazy colors? You got to go fix the mates. Similarly, deleting missing files. This is, obviously going to be very dependent on how many you actually have in terms of those and how you got to delete them. I kind of waited because they were half of them were in sub assemblies, so I would have to resolve those sub assemblies to work on them, and I was trying to get as much performance boon as I could. But the thing I just want to mention here is that when SOLIDWORKS cannot find a component, it has to go through 7 steps of searching for it before it asks you or decides or suppresses it. So if you have a lot of missing components, you got to figure out something to do with these. And this is another one of those, who wants to see these error messages over and over again every time you open it? But you got to either find that component or get rid of it, so it's not searching for all over the place for it. Okay. This is another kind of no-brainer here, but saving to the current version. So everything that Dave had was in 2019. So as I was working on things and saving, a lot of things were just automatically getting saved to 2022, which is what I did everything in. But at some point, I had to get all of the files into 2022. Now, the benefits you're going to see from this, it will definitely vary because it depends on what version you're going into. Is the version you're going to, did they work on performance? So some years SOLIDWORKS puts a lot of work into just performance updates and improvements. And then if you have really old components, then you could see file size decreases and a lot of performance benefits. Now, this is another one of those times that you have an option that will force reference documents to save to the current version, but it's only going to happen if they're fully resolved. So if you can't fully resolve your assembly and then save every single part very easily, then you probably just want to go and throw it into the task scheduler. So everyone has this outside application that installs with SOLIDWORKS. There we go. And the very first option is convert files. So you can basically just give it a folder, and then it's going to start running through those files, opening them up in SOLIDWORKS, saving them, closing them. So this is definitely something to do while you're not trying to use SOLIDWORKS, because it is using an instance of SOLIDWORKS, and it'll slow things down. Okay. Now that all of the kind of of course, things have been taken care of, this is where you really need to start using performance evaluation and assembly visualization to really target areas, because a lot of those things were kind of overarching things or things that were kind of glaring issues that we could deal with. This is when you need to start using these tools to know, okay, where should I spend my time? Because once again, I'm not trying to go through every single one of Dave's parts and optimize every part in subassembly and things like that. And once again, I don't want to replace everything with a big block, which I really wish I had done as a joke for this, but okay. So we have to use assembly visualization to help us out. So where did I go, and performance evaluation. So where did I go first? Well, first I went to appearances. So this is kind of like another one of these maybe weird ones that you might not have thought about, or you might not think is an issue. But if you go and take a look, the number of appearances that some files could have, it could be way higher than you ever would have expected. So you might be looking on here and say, like, there's no way I have a file that has 4,000 appearances. You could have one right now, hiding. And this oftentimes comes from two places. So imported files. So if you have like an old IGES file or something that imported a million surfaces, and it could break up the appearances into a bunch. I mean, it's not crazy to have a complicated imported file that has 10,000 appearances, and if that's in an assembly somehow, it has to paint all those appearances when you go to open it. So how do you deal with this? Well, Dave didn't have any imported parts that I could find. He made everything. So even in that case, how did this even happen? So in performance evaluation, I'll go down to appearances here. And you can see I already did a little bit of work in here, but the nice thing with performance evaluation is whatever you're doing, you can go in and hit open on those files. So if there's a file that has some kind of issue here, then you can go ahead and hit open. It'll go open in the background. So let me jump over there. Alrighty. Now we're not going to talk about the fact that Dave did a bunch of things as multi-body parts, and we didn't, and then never broke them out into sub-assemblies with like patterns and stuff, which is what I would have liked to see. But hey, we won't worry about that right now. So we go through here. We have 41 bodies. This is one of 9, I think actually 10 discs on the suppressor or the compressor here. And if I go to the appearances, okay, I got cast stainless steel on the whole part, no problem. Chromium plate, okay, this looks like a lot, but these are all just the individual bodies, so not a big deal, okay. Then I got another chromium plate. Yeah, okay. So do we think Dave went and clicked on 1,209 separate faces? Probably not, right? So what this really comes down to is oftentimes in your patterns, if you're not really thinking about it, like this thing, it doesn't look like there's even that many faces, but there's a bunch of little tiny filleted faces on each of these fins. So if I like zoom in to this area, you can see there's these little things to fit those in place, and then they're filleted on the edges here. And what happens is Dave did set the appearance originally to just one body, right? Just to that one body. And then propagate visual properties was kept on. So a lot of the options especially in the pattern property managers are sticky options. So they will just stay on every time you use it. So with that on, that is what broke that appearance off into 1,200 faces, right? So that was just the whole issue. It's just that option being turned on. Now, if you have an imported part or you don't really care to figure this out or anything like that, there's 2 ways to get rid of appearances. So if you want to keep display states, then you can always go to the top of your tree and remove all part appearances from that display state. Or if you don't care about display states, it's actually should be faster just to remove all display states from here. Yeah, so that's faster, especially if you have like the imported part problem. You had like 10,000 of them. It is going to be slower to deal with them. So removing them all is probably a good way, and just start over and then add an appearance to like the entire part file, or maybe bodies or something along those lines. Okay. So what's next? Well, we have to figure out where to focus our work here. So let's get into assembly visualization, because I haven't really gotten into it. So assembly visualization, you can see it was already on. So it's on a little tab over here. And what it does is the graphical organization of your assembly. So I have custom little columns up in here right now. So total graphics triangles is all the graphics triangles of all the instances of this thing. I've got my open time. This is me open time for these sub assemblies. As you can see, it's right through there. Number of solid bodies and surface bodies. So those things can also help you with like imported parts once again. So if you're not quite sure at a top level, you can see, oh, why do I have something that has 400 surfaces all of a sudden? And then we can go deal with that. Now, when you open this up originally, it's just going to have mass. So you can go over to the side, you can add columns. You can hit the more option, and that will give you the list of things that you can add to this these columns. And then ultimately, you can save this as a style and then just load that into whatever files you're using. If you create these styles and load it, every time you use assembly visualization in that file, it'll just automatically have these columns. So you won't have to keep changing it over and over again. Other things to note here is that there's different ways of grouping components. So right now I have it in the nested view, which will show me all my sub-assemblies. If I want to see just individual parts, I can undo that to flat view here. Grouping components, I'm going to keep it grouped because I want it, if it's the same component, I want it to be grouped together. And then there's actually a performance analysis button that will just give you total graphics triangles, open time, and then the individual files rebuild times, not the assembly rebuild time, but the individual files. That one's not sticky though, so it'll keep going back to mass if you use that, but it's easy. So other than that, I can click on these columns to sort by whichever column, and then we'll end up getting it to be like color coded based on that column. The other thing that's not super obvious that I really like is if you go down to the very bottom, you can grab a rollback bar of sorts. And if I pull that up, I could say, let's see everything that is above 100,000 graphics triangles, and it'll go and hide all the other components. Now you can see I do have my hidden components loaded, so those will show up. So you can see my number one thing is actually that this 101 fasteners here is the number one single component. If I was having them shown here, but other files here, we can see, and we can see on our screen. Here's some of those cool compressor disks there.
Sean, if I can interject for a second, just because I want to add on this. I see this tool presented all the time as like diagnostics for the graphics triangles like you're showing, but I also use this for some of those steps you did earlier on, like suppressing tiny little components and hiding them.
Yeah.
I'll add a column for volume, and then I'll just sort by volume, and then I can just shift select the tiniest little parts in the assembly. And I think by using this way, the assembly visualization, you can really see exactly what's going on, what you're hiding, and what you want to eliminate and what you want to keep. So just for things like if you're stripping down a model to share a step file or something and you don't want to have all the detail in there, or if you're prepping a model for a simulation, this gives you a lot of options in terms of how to sort and visually see what's going on inside the assembly.
Yeah, no, that's great because it's also because anything too that you're sorting through here, you can create as a display state. Whether or not you want the colors, you can turn those off, or you could have different color system or whatever. But yeah, it's a really good way to save ways to sort your feature tree rather than just always be navigating through your feature tree. So for this one here, let's see. Let me go ahead and go back into my nested view here, which will reset my whole my bar down there. Okay, so, all right. So in terms of dealing with our graphics triangles here and focusing on things, you can see that relatively, even though I have, all those bolts and things like that, once again, I want to do the least amount of work and the least amount to Dave's files here. So the combustor assembly, this big red area, is by far has the largest number of graphics triangles. And then if I open this up, I can see that there is a sub-assembly that it has the largest amount of graphics triangles just for that. So I have this combustor assembly that I can go ahead and open from here, or as Ryan was saying, it's really easy to go and hide, suppress, just do, whatever your selections normally would have been. And then what I'm going to do is I'm going to go over, so let's actually get to the two tools that I use to actually start making some kind of simplified version of these files here. So once again, these are things that you might have run across before, but I'm going to present simplify and defeature. So because they're kind of different, very different from each other, simplify I actually prefer, mostly because it's predictable. So I understand very well what happens when you suppress features or you unsuppress features, and that's all it's doing. So it's easy to use. It's fast, but it's fast for me. So my computer may be chugging along trying to deal with this, if depending on how many features it's going to find. And then the downside is it requires features, right? So it needs to be something built in SolidWorks that it can then turn off those small features. And remember, small round stuff, that's what's really going to be getting you. So in terms of making this, the other reason why I specify on this combustor is there's 6 of them in that assembly. So that's why if I can focus on just simplifying this, then I get 6 times the benefit. So in terms of doing this here, let's go look up our simplify here. So there's 2 options, feature parameter and volume based. Generally, feature parameter tends to find less features in my experience here. So if I go the same options here with that default simplification factor, what this is feature parameters looking at the characteristic dimension of a feature, like the radius of a fillet, versus volumes looking at the volume of the feature. They're both comparing them against the components volume, so whatever component you find that feature in. I also turn on this ignore features affecting assembly mates, but that's just going to affect this assembly's mates, not my higher level ones. So be forewarned, this definitely can cause you mate errors as you're swapping these out in your higher level assemblies. Hopefully, since they're should all be mostly small things, it's usually pretty superficial, and oftentimes that replace references can do a lot to help you. So in this case, the volume option, found 95 features. It's not usually that huge of a spread, not always, 16 versus 95, but generally the volume one tends to find more. I can see what they are. If I want to, select on them, they'll highlight on my screen here. Looks like a bunch of them are for these little fasteners here. And then generally, I could say suppress all of them. And then I like creating the derived configurations. And this is important because this is going to make a configuration for each of the components and then the subassembly I'm working in and activate them all for me. So it does take a second because it has to run through suppressing all those. So I do have a couple already created. And then the way that I like to compare these is still using assembly visualization, but I want to look at it like the top level. So sometimes I just make little dummy assemblies. And I'm not going to save this or anything, but I'm just going to throw them in there. I've got 3 configurations, so I'll activate 3 of these guys here. Okay. And then I can run to assembly visualization. This is one of those times which, I'll just use performance analysis. So this button right here, we'll just pull out graphics triangles, and we can see the difference here. The default has about 180,000 graphics triangles. Remember, we have 6 of these subassemblies. So 180, then we get down to about 145, and then we get down to 23. A lot of this is because of that bolt simplification. But if you actually look on the inside, we can see there's a bunch of patterns on the inside on some of these components here. So that's probably where we're also getting a lot of a benefit here. Now, once again, the reason why I like this tool is because it's predictable, and I don't have to swap out entire components, right? It's just changing configurations. So what I would need to do is I now have configurations to use. Let's actually go off into my combustor here. And all you're going to do is, I would still make a simplified configuration for the combustor. In that simplified one, then I can swap out for my simplified combustors here. These ones did have a mate error. I had one mate, it was one of these like concentric mates or something like that needed to be fixed. And then I was able to propagate that to the other instances. So it was really easy. In this case, I only had to fix one mate, so that's probably worth it. And then ultimately, I need to, in my top level assembly, swap out this big combustor. So remember, I have a simplified configuration here. And I would say, okay, well, let's use the simplified configuration for this combustor. So once again, I wanted to leave the originals alone so I can always go back to my detailed if I need to show it or look at it or do some other kind of evaluation from there. So the other thing that we did was a defeature. So I've actually been kind of defeature resistant for a long time, just because I don't like the original defeature. You create a part from an assembly, which is great, and then you swap that out in the assembly. So if you have purchased components and you really don't need to reference that full assembly that someone might have sent you, that's great. But if you're trying to use this on like your own design, then that's not that great, right? Because I don't like having a separate file out in the ether and then have the simplified part in my assembly, or maybe you have configurations or something like that. But in 2019, the silhouette defeature came out, and that actually gives us the option to just save this as a configuration. So then at my top level assembly, I can have a simplified configuration that references the defeature. I can still have my detailed that references then the detailed subassembly here. And I don't have to do any extra file management or anything like that. So I like that. The other thing that defeature has always been great about is that you don't need features. So unlike the simplify tool, I don't need features. So if I just want to run this on imported parts, then that's great. I can simplify it out. I can take out a bunch of internal detail. That was actually the other thing. It simplifies and takes out the original version. It takes out the insides. So it really can simplify it quite a bit, but that process can take a long time and it can be unpredictable, which is another reason why I wasn't the biggest fan. But the silhouette kind of solves that as well for me. You still should use the original one if you like it, but let's take a look at this. So if I have this component, in terms of what's going on here, if I look at where simplification could happen, just a note here, you can see all of the top, in terms of graphical denseness for these components is fasteners and then bearings, which are, do you need your ball bearings like this, or can we just extrude over the geometry? We won't get into this. Once again, okay, I just don't want to, I don't need this information at that top level. I'm choosing not to use it at the top level. You can decide if you need it or not, but let's go ahead and go defeature. Okay, defeature. Okay, so this is the silhouette method versus the original simplify geometry method. And the silhouette method can still simplify the geometry if you want it to. So if I select this piece, I can tell it, hey, that's basically just a cylinder, and then it'll go and simplify it and give me a little preview. A lot of these simplification methods don't work super great if you can't just like represent the geometry from one reference plane. So a silhouette from one reference plane. But something that's really nice is that there's a none option. So I could just say, you know what, here's some outer parts that I need for mating. Just don't do any simplification. And then the simplifying can be a lot faster. It's just going to essentially wipe out the internal components. And I can still have all my mating surfaces. And then I can go through here and say, create a new configuration, include my top level reference geometry, just in case I need that for mates or something like that. And then I'm just swapping out a configuration at my assembly level. So this works a lot like a speed pack in that you can, there's a update option. So if you change something, you can run an update and it'll go and refresh that. But it has geometry. So the other thing that's really cool is it automatically transfers the mass of the original assembly to this defeatured assembly. So I can still get accurate like mass properties and stuff like that at my main level. So that's why I like it. You can decide if you want to use it or you like the original way or you just don't want to do any defeatures or not. But that was the level that I felt, okay, this is reasonable for simplifying and not messing too much with Dave's things. And I got rid of those dang bearings. So, okay. So that's pretty much it I have for you. There were some honorable mentions that just got left out for this time here that not necessarily something I wanted to do. Some of them required replacing components or speed packs. It's just graphical, so you can get a lot of improvement, but you can't do as much with them. So I kind of avoid them sometimes. One thing that I didn't explicitly show, but I just kept harping on over and over and over again was this. A little bolt simplification goes a long way. So if you have detailed bolts, please stop breaking our hearts if you're talking to any application engineer, you'll just be like, oh no, the detailed bolts here. This is just the combustor assembly that we were looking at here. The difference between having all detailed bolts and non-detailed and just simplified like this was 60,000 graphics triangles. Remember, I was getting all happy about going from 170 down to like 25 or something. And, half of that improvement was just the bolts. So, just something to think about. Ball bearings are the other big ones. Can you just represent them with the inner and outer diameter in a simple cylinder or something like that? Maybe some fillets or something to make sure things fit. But if you can do that, you'll probably be happier with your performance there. Okie dokie. So thank you, folks, once again for being here. I know I really sped through a lot of stuff and we took a lot of time here, but hopefully you can get something out that's actionable for you. You can go and even if, remember, half of those things weren't even things that really changed or affect my file, but I can pull out a little bit of better performance from it. Remember as well that we have two other assembly performance presentations from last year. So if you want to check those out, they're on our YouTube channel with a million other ones there. And this one I'm sure will make its way onto the YouTube as well. And maybe next year we'll have part 3 featuring Gianpaolo Bassi. So send him a tweet, make him get over here into my apartment. If you need to contact us, please. My name is Sean Mars, so Sean M at Hawker System. If you have any questions or you want to talk about this presentation or whatever, or even just make suggestions, hey, do this next year for the assembly stuff. I hope you guys enjoy the rest of our conference here, and you'll probably see me and Ryan floating around. Of course, definitely Ryan, because he'll moderate some more stuff and give his great insight here. But thank you once again. You guys have a great time. Rest of your day. I'll be around here for the next, I guess, 9 minutes if you just want to do Q&A and that kind of stuff. But I'm sure Ryan took care of it pretty well.
A question, kind of logistics here. Are we sharing the PowerPoint presentation, or can we?
I have no idea. Probably. I mean,
Okay.
yeah, there's nothing really in there. I mean, yeah, I can probably just save it PDF and
We can get it up on a link, and for anyone that's interested, maybe just put a message in the chat or the Q&A so we can get your name and at least email it to you.
yeah. I'll start a little notepad here. Yeah, thanks again, folks. Really appreciate it.
I'm just going back through the chat here to see if we missed any. There was, I think, a few general questions on which mates, have the heavier performance penalty.
Mm-hmm.
And I think maybe you talked about that a little bit, but definitely like the mechanical mates, like the screw and pinion and things like that, are going to be, I'd say, the heaviest, and then followed by like even some of the more advanced ones like width, and you mentioned profile center, right?
Mm-hmm.
And then your most lightweight is going to be, two planes coincident, or like my favorite coordinate system. We got a few people commenting with emails too. But origin to origin or coordinate system to coordinate system will fully define a part with just one mate. So that's pretty nice. But when you're considering performance penalty, like Sean was saying, just bear in mind that even though width might be a heavier mate, if it's replacing several mates for you, then it might end up being a wash, and it's also more convenient. So.
Yeah, and the interesting part there too is that, I mean, oftentimes we really are over defining degrees of freedom of a component, even when we're thinking of it as like a normal mating scheme. And so like the classic is like you have a cube and you put coincident on three sides to keep it from moving. You're actually locking down like 9 degrees of freedom or something. But the mate tool does a really good job of solving through that. But once again, it's like that is more that it has to deal with. So the fewer mates that you can get, and not doing things like locking all your concentric mates if you don't need to, that adds more complexity to that mating scheme. Yeah.
But we did have a couple more questions come in.
Oh, okay.
I'm going to put them here just so that we can talk about them. I'm going to put them on the live section. So It's better to mate to planes versus faces was one.
I mean, personally, I like to use reference planes anytime I can, just because you can't delete them. They can't, the default reference planes, so they're not going away, and that's always like my paranoia. I like putting, sketches and things like that if it's convenient. I don't know if there's a actual after that, if there's a benefit other than that you're not going to lose them randomly, right?
Yeah, I would say if it's, if the reference plane is defined for a reason, even if it's one you manually made, then it's great to mate to those because it should be more stable than some random faces on the model, certainly. So just better in terms of design intent even than the rebuild time. As far as rebuild time goes, I don't think there'd be a big difference between the two. But someday you edit the model and the faces might change, and hopefully the plane would not change, right? Because it was
Yeah.
defined, deliberately. So it should be better from just having your assembly not break on you point of view. Um, and then we had a question too: is it a good idea to mate everything, fix the parts, and then delete the mates? That's the really rare situation that I would do that. Maybe only if you were trying to, like I mentioned earlier, like share the part externally to somebody that you
Mhm.
didn't want to have um, all the intelligence of the model.
Yeah, because you might be shooting yourself in the foot with that if you need to move anything at all. Like using mates for positioning, if you are truly just going to fix them, you don't need to, do that. I mean, that's definitely going to help your rebuild performance, right? But you then are not you're not nearly as flexible in terms of updating things in the future. There was definitely a couple of assemblies here that I realized like 10 minutes before the presentation that I had 500 mates in that combustor assembly and I didn't need them right now. So I just suppressed them all and fixed everything just so I could get through this. But that's not like a thing that I wanted to do in terms of if I was actually using that. I would go to creating sub-assemblies first, right? And just try to reduce those top level mates. Because something like the very top level had just under 40 mates. The rebuild time was ridiculously fast. It was like half a second or something. So it's like, I would rather have 100 mates or whatever at the top level and then everything down in sub-assemblies than completely fix things. But if you can get away with it, then, that's definitely good.
I personally try to avoid ever having anything fixed. I don't like it because, again, you can fix something off in space and not do it deliberately, but just have that
Mm,
be, hey, this is the spot I originally inserted the part, and it's been fixed there without any real thought as to where it's related to anything else. So, like I mentioned, like an origin to origin mate or an origin to coordinate system or anything like
mm,
that, one coincident mate is basically going to
yeah.
have similar overhead to fixing it, but then now it's actually in a defined position that you can update if you need to.
All right. Once again, I don't know if there's anyone still out there. Thanks for hanging out and enjoy the rest of your day.